Hello, everybody. Welcome back to Markov Processes. I hope you're all doing well as we finish off our second to last week. I want to put out information on the final soon. It's not cumulative, and I will have review problems to you set by Saturday. And next Monday, we're going to do some new stuff. And next Wednesday, we may take a little time to finish up, but mostly review like before a normal exam. And just like before a normal exam, I'm probably going to hold some additional reviews between the final class and the final. Yeah, so let's talk about that. And then we're going to get back to the Gibbs sampler. So come on, tablet. In 5, you've got some kind of process and you're given a particular kind of time embedding. And we're kind of want to explore, we want to explore whether or not the discrete time process is going to have the same stationary distribution as the original process. And it doesn't. It depends on where you embed the process. So, okay, so we are talking about, come on, 5 on the homework. And this is where we have a machine that's either in state 1 or state 2. And I do use the word departure in the problem in quotes because I mean going down or going up. Yeah. And so this has, it's in state 0 for some time, and then it jumps up and it's in state 1 for some time, state 0, state 1. You're just going to keep moving between state 0 and state 1. And the first question, we want to know the distribution of this machine state. And this is in equilibrium. This is a stationary distribution because otherwise I'd have to give you a starting distribution. You wouldn't be able to find the distribution at some given time unless I told you how we start the chain. Like maybe we start here 1/3 of the time and start up here 2/3 of the time. So this was meant to be a stationary or equilibrium distribution. So we are going to look at the chain just after departures, which means, here is a departure. So there's one person and they depart, and just after they depart, there's 0 people. And here's another departure. There's one person there, but just after they depart, there's 0 people. And we could even start this, let's just say we're going to start our chain here. So this makes a new discrete time Markov chain, which in this picture is always 0. But in fact, in any picture, it would always be 0 because for this model, we can only take on the values 0 and 1. So every time we have a quote unquote departure, I say that because it's not really customers, but we drop down to 0, we are always finding ourselves at state 0. So I don't know what you want to call this distribution. You could call it pi. It's going to end up not being a stationary distribution, but that's okay if you want to call it pi. I would maybe just say the probability that you're in state 0 in equilibrium or really any other time you want to look at this post-departure chain, you're always in state 0. So that probability is 1. And the probability you are in state 1 when you look at this special discretized yellow chain is always 0. Okay, so in B, you want to talk about whether the distribution that you found here is going to match the stationary distribution. And in B, you could find, but you don't have to do this. You could find pi 0 and pi 1. You could treat it as a birth and death process. If you really want to, really solidify this in your mind, you can actually find values for pi 0 and pi 1. And they're not going to be 1 and 0. And I can tell you that from the beginning, because as long as there are some real rates of transition, I guess we can make a rate 0 so that we never leave one state. But in the long run, this machine is sometimes in state 1 and sometimes in state 0. So we expect the stationary distribution to give us the proportion of time we're in state 0 versus state 1. And we don't expect to see this kind of thing. And finally, has the pasta property been violated? We looked at three kinds of time embeddings. One was to look at the state of the process every time something happened. Another was to look at the state of the process. So that was not pasta. That was what we called the time embedded jump chain. The pasta property says that we can look just before arrival. So we can look at the process right here just before we jump up. And we can look at it here just before we jump up. And you can see, I don't know if you can see this color, but it's not that important. We're also getting a zero chain. And pasta says that this is supposed to, this and the post-departure chain that we're looking at in this problem, the stationary distribution for these discrete time chains are supposed to match that for the continuous process. So if you actually find these, it's supposed to match. But the P in pasta, actually the first PA stands for Poisson arrivals. And that pasta property depends on the arrival process being just a Poisson process, which has a constant arrival rate. But the arrivals are kind of locked out here once you have one quote unquote person in the system, because if you get to state one, you cannot go to state two. So this is not like just an unrestricted Poisson arrival thing. It's a birth and death kind of arrival process, but all the birth rates are zero after a point. So the pasta property has not been violated. We have talked about how the true continuous stationary distribution is supposed to match that of this discrete chain, but the PA in pasta means Poisson arrivals, and we don't have that. We have like a restricted kind of Poisson arrival process. Okay. So yeah, I have another problem in the chat about 6. And we have cars arriving to a car wash and then getting locked into a track. And so the car wash is like the server, and cars are arriving according to a Poisson process. And then the service times are not exponential. They're not uniform. They're actually deterministic. They're always 3 minutes. And we want the expected number of cars in the system in equilibrium. So if you think of cars lined up and then going into the car wash, this is a queuing model, but it's an MG1 because the service times are not exponential. So if you let S be a typical service time, you had a problem earlier where S was gamma with parameters alpha and beta. In this case, S is always 3, but that is a probability distribution. You can say that S is 3 with probability 1. So so the expected value or mean for S, it's always going to be 3. I mean, what do you expect 3 to look like the next time you look at it? 3. And there's no variability in what you're going to observe. You're always going to observe 3. So the variance of S is 0. And we have a formula for the expected number of people or cars in the system. This is an expected queue length where we're talking about everyone in the system, including the person being served. And that involved calling this variance. We called it sigma squared. And this expected value was actually 1 over mu, even though mu is always an expected value in statistics. For us, it's a rate. And then you have a formula, and it's just plug and chug. And this N is the number of people that arrive during a service time. So the service time is 3. So N is a Poisson random variable, not a process, but the number of arrivals during a period of length 3 is Poisson with parameter lambda times 3. And lambda here is maybe 8. The Poisson process is arriving at a rate of 8 per hour. But one thing you do want to be careful about in this problem is one rate is given in hours and the other is given in minutes. So you want to convert all to 1 unit of time and work in one of those. So this might be 24 if you are working in hours, or it would be 3 times 8 divided by 60 if you're working in minutes. But you just want to use our formula. And the expected value, let's say you're working in minutes, maybe lambda is 8/60th of a minute. And that means that n is Poisson with parameter 8/60th times 3. So 8/20th, 2/5. The expected value, by the way, when we derived this formula, we also derived a formula for this. If you want to look that up, you can do that. But this one's not so bad. This is the variance for n plus the expected value for n all squared. And the variance for a Poisson is the parameter. It's the same as the mean. So the mean is the parameter squared. And you don't have to simplify. And you will be given this length formula on a cheat sheet for the final. Okay. So yeah, I will have a little time to stay after, so I want to get going in the lecture so I don't get more behind. I just got a direct message, an interesting question about will there be homework assigned for next week? So homework 10 is officially the last homework, and you are getting to drop your 2 lowest scores. But I'm putting out one more that is optional. And but in putting this out, I'm going to drop your 3 lowest scores. So if you're happy with how your homework's been going, then I wouldn't bother with 11 unless you just want to do it for fun or review. But it's a chance to wipe out another low score or 0 if you have one of those. So there will be a homework assigned. It's completely optional. If you do it, you can drop 3 out of 11. Okay, I think I'm caught up on the chat. So let's go back to the Gibbs sampler. The Gibbs sampler is an MC algorithm that stands for Markov chain Monte Carlo. And that means you probably have a distribution that you want to draw from. You don't have a Markov chain. But just like with the Metropolis Hastings algorithm, this is something that creates a chain for you that will be converging to your target distribution. That's called the Gibbs sampler. And your target for a Gibbs sampler is some pi. And we're going to create a stationary distribution that has pi as its stationary or limiting distribution. But one thing about the Gibbs sampler is you need something at least 2-dimensional. So I think last time I wrote it as k-dimensional, where k is at least 2. I guess you actually can do it one-dimensionally, but that would involve drawing from the target distribution and starting state. You could sort of make a silly example out of one-dimensional. Forget I said that because I think that's just confusing. But to run this, we're creating a chain, as I said, and these points on this chain are representing like an x1 and x2, maybe if I'm doing it in 2 dimensions. And this is like an x1 and an x2. And we're using notation where we want to talk about a point at time 0 and a point at time 1. So even though I wrote this, I didn't leave myself with a lot of space, but I'm using a common notation in Gibbs sampling, which is to put a 0 in a superscript for time 0, and then a superscript of 1. Did I just say in a superscript? I mean, in parentheses. It doesn't look like powers because we have subscripts on the x's, so not so nice to put time there. I mean, you could say x1, at time 0, I guess, but this is the more common notation for Gibbs sampling. Anyway, you start your chain at an arbitrary point. And so I'm going to call this, for k dimensions, I'm going to call it x1 super 0, x2 super 0 out to xk. And get rid of this, you are in my way. And so you can move to the k-dimensional point at time 1 by going through a sequence of steps. And if you know how to move through any step, then, that's good enough. So let's assume you got out to time n and then talk about how to go to time n plus 1, but n could be 0. So suppose you're at time n and you've got a point x1 super n out through xk super n. Those I'm writing as lowercase because they're already fixed values. But when we talk about drawing a value from a distribution that's still random, it's not that important, but I like to make these capital. So draw or simulate x1 at time n plus 1 from the conditional PDF for x1, given all the rest of the values that you've already fixed. Yeah, let me take a second to remind you that we're using this abusive notation, but it's actually quite wonderful, because otherwise it would be crazy. If you see in what I'm about to write, like pi x2 given x1 and x3, this represents the conditional PDF for x2 given x1 and x3. Whereas if I write pi of x3 given x1, x2, if you're being literal about this, these look like the same function, just plugging things in different places. But this represents the conditional PDF for x3 given x1 and x2. So really you would have to write something like x1 given x2 given x1 and x3, and then like the arguments, but that gets crazy. So we are using the arguments here to tell us what PDFs we're looking at. And I'm going to have some y's in this. Am I going to have y's? No, we don't need the y's anymore. Never mind. I needed those for my proof. So, okay, that said, we're going to draw the first value of the first coordinate of our next point from the PDF for x1 given. I'm going to take the rest of them that I've already fixed. So x2 super n out through xk super n. And I didn't put a super n here because it's a PDF. I'm looking at it over all x1 and I want to simulate from it. And I know some of you are thinking, when can you possibly do these kinds of draws? And yeah, I'll try to convince you that you can, but then you draw. Well, you can't always, but there are cases where you can. So then you update x2 by drawing from the PDF for x2 given the other x's, but you've already updated x1, so you want to plug in x1 that you got from your draw in the first step, and then go to x3 that you haven't updated, so I'll take it from time n out through xk to time n. You just plug in the other x's and you use what you have at that point. I'm not doing it here, but a common notation if you're trying to read about the Gibbs sampler is x minus I, and this represents the vector where you've removed the ith component, which is a kind of nice notation, but I thought I would try to keep it more like a notation. Okay, so you continue, and finally you draw xk at time n plus 1 from the conditional PDF for xk given the other things, and the other things have all been updated to time n plus 1. So all of these are going to have n plus 1 in the superscript. I'm just going to go up to xk minus 1, n plus 1. And that is how you move from a point at time n to a new point at time n plus 1. Let me know if that doesn't make sense. I'm going to look at an example. The Gibbs sampler is really important if you are doing Bayesian statistics. We're not going to talk about Bayesian statistics other than this little conversational blurb. So if if you are a Bayesian and you have a PDF and you look at a bunch of data that comes from maybe IID realizations of a PDF, and you write down the joint PDF for all of your data, which if they're just independent realizations, then you're going to be multiplying an individual PDF. But our PDFs depend usually on parameters like a lambda or an alpha and beta. And if you are approaching this as a Bayesian, then you treat the parameters themselves as random variables. And that means you need to give the parameters their own distributions. And you can do that if you have some expert knowledge about the system, but you can also give really non-informative sort of PDFs like if your parameter is a P from the binomial NP or the geometric P, something between 0 and 1, you can say, I'm going to assume that P is uniform on 0 to 1 because I really don't know anything. But if you're treating them as random variables, you can compute the conditional PDF for the vector of parameters given the data you observed. And if you want to make inferences about those parameters, then if the vector, if that PDF of the joint PDF for the parameters after, given the data, is not very tractable, you might need to simulate from it to compute, like, what is the average value of my parameter alpha in my model. Maybe I should have written stuff down. But yeah, I'm trying not to go there. But in Bayesian statistics, you often can compute and draw from these kinds of conditional PDFs. But let's just do an example that's not really from anywhere. I just made it up. So I'm going to have just 2 dimensions. So pi of xy, it is proportional to xy and then e to the negative xy plus x plus y, all in parentheses. So they all get hit by that negative. And x is greater than 0 and y is greater than 0. It's not important that we know the constant, but I did integrate it so that we could check. So this integrates if you let x go from 0 to infinity and y go from 0 to infinity. It integrates to approximately 1.9269, which means that the PDF is going to be 1 over 1.9269 xy e to the blah, blah, blah. We don't need that for the simulation at all, just to check what we're doing. And let's just find a marginal to check. So the marginal PDF for x, say, I don't really care about this constant right now. I just want to take this, there's a constant. You could put a c in front of it if you want. But if you integrate out y, so pi of x is kind of like equal to, but really proportional to if I'm missing the constant. Integrate out y, xy e to the minus xy plus x plus y dy. First thing I would do would be to take out all the x stuff. So there's an x, and like this x, I can pull out e to the negative x, integral 0 to infinity, y e to the minus, and then I have 2 things in the exponent with y's. So I'm going to write this as x plus 1 in parentheses times y dy. And to integrate this, note that it looks like a gamma distribution. If as a function of y, this looks like a gamma with parameters 2 and x plus 1, because the PDF for y, if it was a gamma alpha beta, would be 1 over the gamma function of alpha, beta to the alpha, y to the alpha minus 1, e to the minus beta y. So I got my beta, from the exponent, and the y to the alpha minus 1 is y to the 1, and that's why alpha is 2. So to integrate this without integrating, I've got x e to the minus x and an integral I want to put in 1 over gamma of 2, which is really doing nothing because gamma of 2 is 1 factorial. I do also want to put in beta to the alpha, so that's x plus 1 squared, and write the rest. Again, this has nothing to do with the simulation. We're just finding some distribution so we can look at our results. And then out here, I'll compensate. And then this integral is 1. So the pi of x is going to be that constant 1.19269 x e to the minus x 1 over x plus 1 squared, because gamma of 2 is 1, on x greater than 0. Okay, so how do you find the conditional distribution for x given y and y given x? Fortunately, you will not have to do what I'm about to do because this takes a while. I want to convince you that there's an easier method. So the conditional PDF for x given y is supposed to be the joint PDF. Actually, I didn't find the marginal for y, so let me turn this around. Let's look at the conditional for y given x. It's the joint PDF over the marginal for x. And this is the 1 over 1.9269 xy e to the minus xy plus x plus y, all over 1 over 1.9269 x e to the minus x 1 over x plus 1 squared. And if you cancel things, you cancel this x and you cancel this e to the negative x with this part, you are left with x plus 1 squared times y times e to the minus x plus 1 y. This is a proper PDF because I used a proper PDF in the numerator and the denominator. This is a gamma. This is 1 over gamma of 2 because gamma of 2 is 1. X plus 1 y. But I guess I don't want to talk through the steps, but if you think about what we did here and a little slower, I think you can convince yourself maybe that as a function of y, pi of x is constant. And what you can do to more quickly find the conditional PDFs is this. So I wouldn't actually go through all that. Here's my target, xy e to the minus xy plus x plus y on x greater than 0, y greater than 0. If you want to find the distribution for x given y equals y, all you need to do, you don't have to integrate anything. All you need to do is look at this and drop constants of proportionality when you're thinking of it as a function of x. So as a function of x, this y is a constant. Like once it's given, it's a constant. So if you just look at the x stuff, you have x e to the minus xy plus x. And if you separated this out and had an e to the minus y, that's also constant. So I'm just looking at the given PDF, but I'm treating the y's as constants. And this is x e to the minus y plus 1 x. And that's enough to figure out the distribution of x. You would have to put in the right constants, but this is a gamma distribution again. So the distribution of x given y equals y has a gamma distribution with parameters 2 and y plus 1. Yeah, this isn't a proper PDF, but we can turn it into one. And we already saw it, but you would do something very similar. I mean, this function is symmetric in x and y. So we know that y given x equals x is gamma 2 y plus 1. So those are the distributions we have to draw from back and forth in the give sampler. And For this, I would definitely use a built-in gamma distribution generator. We didn't do that in the past because our goal was to simulate values from kind of simplistic or like one-dimensional distributions, and we wanted to know what was going on under the hood in our software. But now our goal is to simulate from something more complicated. So if you have something that will allow you to grab a gamma out of the software, by all means do it. So
that second one should be x plus 1,
oh,
right?
yes, it should. Thank you. This should be x plus 1. Thank you. Thank you. Let's go to a simulation. Okay. What you're going to see first is me just following the marginal PDF for X, which if I was trying to assess convergence here, that would be dangerous because the marginal PDF for one of them could converge when the other one still hasn't, or overall the joint PDF hasn't. But let's just look at, okay, so I started a chain. Actually, I originally started it at XY equals 1, 1, but it converged way too quickly to be interesting. So, oh no, I did that here. Oh no, did I do it? Oh, no. Okay, this is a histogram, this blue thing that's cut off on top because I was trying to keep the y-axis constant through my simulation. And my bins have width 0.2. And I started with both x and y equal to 0.01, only to make this take a couple of steps longer to converge because it converged too quickly when I started at 1, 1, and I want you to see that action. So right now I have 100,000 x's and y's, and they're all 0.01, 0.01. And if you make a histogram, they're all in my first bin. And so I have a really tall bin here. But let's go forward one step with the Gibbs sampler. So you can already see that we've kind of taken on the shape. So that's x and y at time 1, the superscript 1. That's 100,000 values. Let's go forward another step. It's getting really close. The thing is, when I started at 1, 1, it was already there. And so you didn't get to see the fun, like, oh, it's morphing closer. Third step, that looks pretty good too. It's still a little iffy at the top. You would like the lines to sort of be going through the centers of the top of the rectangle, but you may never get there at all if you don't have if you don't sample a lot of values. So I have 100,000 values, so I can get a pretty good picture. Let's go again. Oh, almost. Yeah, I mean, maybe done. That kind of looks like the curve is in the middle of the line, but not so much this one. That's not a convergence diagnostic, by the way. So it does look like it's kind of staying there. And if you're just eyeballing it, this is totally going to be dependent on the bin widths that you choose. But it looks like the marginal PDF for X1 converged pretty quickly to the true marginal PDF for X1. How did I get the marginal PDF in the histogram? I computed 100,000 pairs of X's and Y's, and I just made a histogram of the X's, ignoring the Y's. So that's what's going on here. I want to look at this in 2D. So let's do that. What I have here is the joint PDF, pi xy, properly normalized with the 1.9 something, graphed as a surface. And I made a histogram. U is X and V is Y in this, but I binned up this plane into squares with length 0.2, side length 0.2. So I binned up the x-axis 0 to 0.2, 0.2 to 0.4, etc. Same for the y-axis. And I made histograms. So I made cubics, like rectangles in 3D that represented, whose volume represented the proportion of outcomes I had in the square. And that was really too messy to look at. But what I have graphed here is these dots are the tops of the histograms when Y is between 0.6 and 0.8. So if I turn to look at the x-axis, or was it the other way around? The other way around. If I can get this lined up, so it's totally on a line there. Okay, this is my x-axis. Yeah, it's the other way around. So x is between 0.6 and 0.8, and I made like a histogram in there. So a bunch of rectangles if you looked this way, but I just showed the tops because originally I was trying to show you everything and it was really messy. So it's hard to tell if that's on there. It actually is. It looks pretty good. Because the surface, this is coming down. It's not supposed to match this curve. It's coming down the surface over here. Let's look at a different, I want to look at the bins between 0 and 0.2. So I'm changing up my code. Okay, that doesn't look as great, but the reason is it's a histogram with a lot less values in it, because out of my 100,000 values, about 7,000 of them had an X between 0 and 0.2. And so this represents the tops of a histogram made out of only 7,000 values. So that's not going to look as smooth. And so let me really quickly simulate with more values. I'm going to go up to 500,000 values. Hope this doesn't take too long. Oh, that was pretty fast, even in R. And I'm going to make this same plot again, see if it looks any better. See, you can see that curve looking a lot nicer. So those are all the X values that are between 0 and 0.2, and then we made a histogram over the Y values. And it's probably hard to see here, but there are like these little curves showing you, trying to depict the surface. And this is actually matching pretty well. But there's no way I would just eyeball this. I would eyeball it to know I'm doing my simulation right. And then maybe come up with some other diagnostic, which we're going to talk about. But that is, yeah, I think that's all I want to say about that example. The give sampler in 2D. So let me go back to sharing my screen. Oh, I forgot the simulation break song. What I'm about to do now is talk about a convergence diagnostic. I'm going to talk about it pretty quickly because it's not, I have more things, actual Markov things we need to do. And I also think not everyone is going to understand this because you need to have some stats, either math stat or stat, because I'm going to talk about some unbiased estimators. So I'm going to go pretty quick, but just so you know, and you can look it up yourself if you want to use this. It's called Gelman and Rubin's R statistic. Okay, so here's Gelman and Rubin's R statistic, and kind of brief. What you do is you run, I'm going to draw it in one dimension, but you take a lot of starting points that are really spread out. Technically, they need to be quote unquote over dispersed with respect to the distribution. So like if the distribution you're going, like you just want to take them spread out. I mean, I have no scale here, but you don't want to just take a bunch of points all close together. And so you run M chains, usually using the same random bits for each chain. You know, when you go forward, you draw a uniform and they're, and so you use them to run each chain. So you run M chains from so-called over dispersed starting points, and you go for a long time. And this statistic is supposed to tell you how long to go for, but you do pick some number to where you ignore the beginning, this kind of burn-in period. You could not pick that number. You can start from the beginning. And then you start collecting values here for each chain. And so you collect, I'm going to say n values for each chain. And so like, it's not rum, this is run. So if this has reached its stationary mode, then all of the values like this and this and this should be coming from a stationary distribution. And this and this and this as well. And this and this and this, they should all be draws from the stationary distribution. And those points should be statistically indistinguishable. So you compare the variance of like the variability of the points in a chain within the chains to kind of an overall variance of all the points if you lump them all together. And so if you talk about your data as like x11, x12 out through x1n as being the n values you draw from your first chain, and x21, x22 out through x2n to be your n values from the second chain. And we've got m chains, so xm1, xm2, xmn from the mth chain. Then you can compute if you don't know what I'm talking about, don't worry about it, Sj squared, the sample variance for the jth chain. And that is going to be, you're going to sum over all, what letter can I use? Use my J. I'm going to use I equals 1 to n, xji minus xj bar. And by that, I mean the average, the sample mean of everything in the jth chain, and divide by n minus 1. And if you've had stats or math stat, you know that we're not dividing by n because you want an unbiased estimator. See, that's why I'm going a little bit off the rails here. So let me just wrap this up. You average those. People call this W. So J goes from 1 to M. So you average these. And that is one estimator of the variance of these points that are supposedly all coming from the same distribution. So now I'm going to go quicker. This is called the within chain variance. And then you compute something called B, which is called the between chain variance. And I'm just going to cut to the chase on this one. This is, you look at the sample mean for each chain and the overall sample mean. And then you look at the sample variance of that data. You know, you've got M different sample means. And so it's a variance of M things. So it should have an M minus 1 under it. And so I'm going to write this as J goes from 1 to M, xj bar, meaning the mean in the jth chain, minus x bar, meaning the overall mean of all m times n values squared. That needs to be divided by m minus 1 if you want an unbiased estimator. And I don't have time to really talk about this, but it also needs to be multiplied by n. Some of you know that the variance of a sample mean is the original variance for the individual data points divided by n. And this is supposed to be an estimate of the variance of the individual data points. So I do need to adjust, and this is a longer conversation. Anyway, yeah, I'm spending too much time on this. So estimate the variance of the stationary distribution pi as, I'm going to call this v hat, like pi, as a linear combination of these two variances. I want to say, oh, I'm just going to write this up later, but I'm not sure I can. I'll try. That's why I'm still talking about this. If your data, if your X's are really drawn from the stationary distribution, you can show that this is an unbiased estimator for the true variance of the stationary distribution. I gotta finish this off. You compute something called the potential scale reduction factor. This is the R statistic, Gelman and Rubin's R statistic. R hat is the square root of the estimated variance divided by the within chain variance. We can show that this is greater than or equal to 1. And if the chain is converging, you want this to be going to 1. You want the variances. This is one estimate of the variance for your stationary distribution. This is another estimate, which was built out of a weighted average of 2 estimates. And so we could show that this ratio is greater than or equal to 1 and goes to 1 as your chains, as n goes to infinity. So I looked all over for it, but I couldn't find it. I have a really cool visualization. I worked at NCAR, the National Center for Atmospheric Research, for a long time ago, and they were doing a Gibbs sampler on a 30,000 dimensional chain. And they wanted me to come up with some kind of visualization for them to show that their Gibbs sampler had converged. And it was really fun. I wish I could find it. I certainly didn't have enough time to reproduce it. So I made a grid and it was really big and it had 30,000 squares on it. Actually 29,000 something. And I made like a heat map where I had some red colors here and some blue colors here and some gradient. And blue corresponded to, so I computed an R for each one of these parameters. Each one of these 30,000 things had many parallel chains run and computed an R, and blue represented 1 and red represented something huge, 1 million. I don't know. I don't remember. So you started out in my visualization with a big thing full of red cells. And then things started flipping around and blue started coming into it. And we ran the chains until the entire thing was blue. And we were saying that it cooled to blue. And so when the entire thing was blue, that represented 30,000 different values of this R statistic being close to 1. And it was a lot of fun. I really wish I had that. It was cool. This is the same thing. Someone asked me, is this the same as the convergence statistic or are they different? So the convergence statistic is that R hat. And in this particular picture, I've computed 30,000 different R hats because I am running multiple copies of 30,000 dimensional things in parallel. I have to get back to Jackson Networks. I'd be happy to talk to anyone about this more. Let's chat. So let's go back to Jackson Networks. This is the final thing on the final. As usual, we're going to do some new stuff on Monday and then mostly review on Wednesday. Let's find a stationary distribution to remind ourselves what we were doing. So here is not the same one, but a 3-server station. And this is the first box over here is going to be server 1. And we'll know that because I'm writing service rate mu1 in there, service rate mu2, service rate mu3. And people come in from outside. And the networks we've already talked about have been a single stream Poisson process, and then some probabilities that route them to get in line at the different places. I am going to make this one look a little bit different. I am going to just say that people arrive to the different servers from external processes. So they arrive here with some Poisson process with rate lambda 1, and they arrive from the outside with some other independent Poisson process with rate lambda 2, and over here, rate lambda 3. So because we have lambdas in our formula for the stationary distribution of a Jackson network, those flow balance equations, I am going to rename these. I'm just going to call this phi1, phi2, and phi3. But I thought it was worth writing the lambdas first because these are our usual input rates from Poisson processes. So the overall external input rate, or the overall external input process by superposition, is a big fat Poisson process with rate phi that you can get from adding these three together. So it looks a little different than the networks we talked about last time, but it really is the same thing. We can just have them come in one stream and then route them with routing probabilities. And where can we route in the system? I'm gonna have to refer to a picture because I already computed some stuff. You don't want to see me do this live. So maybe when they finish at server 1, they go back in line to server 1 with some probability P11. From 1, they can go to 2 with some probability P12, and from 2, they can go to 1. So I usually draw this as coming out here and going in here, but that's way too messy. So if they go to a server, they get at the end of the line there. You know, again, a person leaving here would go in there. And we can go back with some probability P21. And from 1, I could go to 3 with some probability P13. And from 2, I could go to 3 with some probability P23. And I will leave the system if I'm at server 2 with the remaining probability. So this is going to be like a P20, and P20 plus P23 plus P21 have to be 1 because those are all the choices you can make if you're leaving server 2. And let's say we leave with probability 1 here. So from server 3, I'm not going anywhere else but out. I'm sure you didn't get that picture, but let me write down all the parameters for you, and that's enough to describe this. So I am going to use numbers for once. The external rate to server 1, I'm going to say is 2 per whatever units of time. The external rate to server 2 is 3. The external rate to server 3 is 1. And then the probabilities that I had on here, P11, I'm going to let be 1/8, P12, 5/8, P13, 2/8. So in my picture, you could not leave the system from server 1, and that's why there's no P10. If there was, it would be 0. We do have the probability of coming from the outside to server 1. It wasn't given in the diagram, but that's going to be the rate of input to server 1 as a proportion of the total rate of input. And using the numbers I have already, this comes to 2/6, which obviously is 1/3, but I want all the denominators to look the same. Okay, so starting from 2, I can go to 1. I have P21, and I'm setting that. I'm making these up to 4/12. And P23, the transition probability, if you end at 2, that you go to 3, I'm going to make that be 3/12. From 2, you couldn't go back to 2, but you could leave. So P20, I'm going to make that 5/12. And finally, I don't need a transition probability from 3. P30 is 1. And the external arrival rate to 2 is going to be phi2 over the sum. And that came out to be 3/6. And the last one similarly turned out to be 1/6, or you can just add them. All right, these are the parameters that I'm giving. So if you have that, you don't need to see the picture anymore, although I think the picture is helpful. So my question is, what is the expected total number of the customers in the entire system in equilibrium or stationary mode? I'm going to let Ni be the number at server I. This includes the one in service. In this picture, I have 3 people at server 2. There's 1 in service and 2 waiting. And we are going to find the joint probability for N1, N2, and N3. And then we're going to use that. Our answer is going to be, right answer in front of this. Our answer is going to be the expected value of N1 plus N2 plus N3, which you can get using the 3-way joint PDF, but we don't need to because expectation is a nice linear operator. Okay, so to find this, I could remind you of Jackson's theorem, but I want to, in the interest of time, I'll just state it when we get to it. But we had to solve what are called flow balance equations. And so if this thing is in equilibrium and balance, the rate in and out of each server should be the same. So we let lambda I be the rate into and out of server I as I goes from 1 to I is 1, 2, or 3. This is the reason my external Poisson processes, I didn't use lambdas because it would be confused maybe with this. I am going to grab my picture. I think it's going to be maybe easier here. All right. Well, we won't completely see it. So lambda 1 is the rate into server 1 or the rate out of server 1. Right now, I'd like you to think of it as the rate out of server 1. It needs to total the rate into server 1. And from the picture, you see that we can get to server 1 from the outside, and we can get to server 1 from, what am I doing? That's not server 1. From the outside, this got erased, and we can get there from server 2. So this is going to be that outside rate, V1, and then, we can also get there from 1 itself. So the output rate from server 1 is this lambda 1. And I need to send this proportion back to server 1. So the rate out of server 1 thinned into the actual people that go back to server 1. And then finally, the rate out of server 2 thinned into how many, the proportion of people that went from 2 to 1. That makes sense? Tell me if it doesn't. And there was no way to go from 3 to 1. Okay, server 2, I'm going to speed this up. There was an external arrival rate. So this is supposed to represent the rate into server 2 or the rate out of server 2. So the rate out of server 2 needs to be equal to the rate into server 2. And we've got this rate from outside, and we can come from 1. So there was some rate of departure from server 1 times the probability we go from 1 to 2. And finally, lambda 3 is phi3 plus lambda 1 p13 plus lambda 2 p23. And then all of these together, because you were given phi1, phi2, phi3, and the p's, I could actually find lambda 1. If I plug those numbers in, I still have like a unknown lambda 1 and lambda 2 on this side. So you do have to then solve. But I got lambda 1 is 9/2. Lambda 2 is 93 over 16, and lambda 3 was 229 over 64. So to finish finding the stationary distribution, since we are doing this numerically, I do need some numerical service rates. So let's say that we were given that the rate at server 1 was 5, the rate at server 2 is 6, and the rate at server 3 is 4. I am going to need those rates to be larger than each of these respectively, or I'm going to get a backlog. And I did check these fractions. I don't remember what they are, but I did choose some service rates so that individually they are larger than these 3 things. So Jackson's theorem says that the three-way joint PDF N1, N2, N3 looks like an MM1 for each server. This is going to be 1 minus, since we haven't recapped it today, I'll say lambda 1 over mu1, lambda 1 over mu1 to the N1, the same thing for N2, multiplied by the same thing for N3. And with our particular stuff here, this is 1 minus, I should work these out. Lambda 1 over mu1 is 9/2 over 5, so that's 9/10. And I'll just state the others. Lambda 2 over mu2 is 93 over 96. Lambda 3 over mu3 is 229 over 256. I don't know if you can read that, but that gives us the parameters for those three geometric looking things. So 1 minus 9/10, 9/10 to the N1 times 1 minus 93 over 96, 93 over 96 to the N2, 1 minus 229 over 256, 229 over 256 to the N3. And these n's can take on all values that are non-negative integers, so 0, 1, 2 on up. There's the big joint distribution. And to find the individual expected number at each server, including the one in service, if you were trying to find the distribution for the number of people at server 1, you would sum out N2 from 0 to infinity and N3 from 0 to infinity. But if you put this here, then this has no N2 and N3, so it would be pulled out front, and you'd see that the rest of it sums to 1. So the marginal PDF is 1 minus 9/10 times 9/10 and 1. This is a geometric. The number of people at server 1, including the one in service, is the geometric, the one that starts from 0, and P is 1/10. Yeah, P is 1/10, because that usually looks like 1 minus P to the X times P. So this is the P. And the expected value of that geometric is 1 minus P over P. And that is 1 minus 1/10 over 1/10. That is 10 minus 1 over 1, and that is 9. Doing the same thing with the others, using the fact that they are also geometrics. The expected value at N2 I got was 31, and the expected value at N3 was approximately 8.48, which makes the total N1 plus N2 plus N3 approximately 48.48. That is the expected number of people in the entire network in equilibrium. What does it come down to? It comes down to identifying parameters, writing down the flow balance equations, solving for those lambdas, and then sticking it all into a geometric looking product formula. Can we find the expected sojourn time for a customer in the entire system? Sojourn, remember, means not only their time waiting in line, but their time in service. So if this system is in equilibrium and someone arrives, let's say these servers are all in the lobby of a building. So someone comes into the building, and when do they leave the building? Assuming they're not going elsewhere in the building. That includes their service times. And we can't compute the expected waiting time at the queues. And the reason is because a typical customer does not have to visit all three of those stations. So it's really hard. But Little's law applies here. And that was L equals lambda W. And in that horrible notation, W was the expected sojourn time. And L was the expected queue length or number in the system. And lambda was the overall input rate. So the expected number in the system was our 48.48. Our overall input rate was 2 plus 3 plus 1. That's the sum of those input fees. And the expected sojourn time is what we want to find. And if you do this, hopefully I didn't make a mistake when I did this, I got the sojourn time of approximately 8.08. So if this was all given like rates in minutes, the expected time a customer spends in the building with the 3 servers, assuming they're not hanging out in the building, is approximately 8 minutes. Yes. Okay, so I don't have that much time, but I do want to get started for the purpose of forward momentum for our almost final topic. Our final topic is going to be perfect simulation, which is not going to appear on the final. We're going to talk about that Monday. But our almost final topic is a closed Jackson network. So this is just the teaser. I will write this out formally next time because I don't have a lot of time, but you've got servers and you have routing probabilities and you have, I don't know, you don't have to be able to go everywhere, and you have service rates. And we want to find the stationary joint distribution for the number of people at each station, but they're fixed. No one comes in and no one leaves. And a good example of when this might, so you always have like N1 plus N2 plus N3 is some kind of constant. I have a couple of good examples for this. My made up example is you're on a factory floor and you are moving between stations or you're making a product and you're moving things on pallets and you only have a finite number of pallets and they just keep ending up at different stations. But overall, they're moving around with the same number of pallets. My better example, I think, is what I'm doing currently in my research, and it has to do with chemical reaction networks where people are molecules. And we'll talk about that next time on Markov processes. So I just saw the chat. I don't know. I don't remember the date of the final. I will look it all up and put it in the announcements right after I'm done here. So next time we're going to get the stationary distribution, and then I'm going to just tell you we're going to have fun with perfect simulation, but that won't be on the final, where we get to see infinity.
Hey, Jazzy, want a cracker? Cracker? Hey, Jazzy, do you like Markov chains?